The Zoom session is being brought to you by the Fractal Horizon Forming. All right, for today, 1-5 complex numbers and 1-6 solving equations beyond the quadratic, or certain equations beyond the quadratic. All right, we start with complex numbers. Starts off by adding a new solution to an impossible equation. Solve I squared equals -1. A positive number squared is positive. 0 squared is 0, negative squared is positive. So none of those, positive, negative, or 0, squared to a negative number. So therefore this solution I is neither positive, 0, nor negative. So okay, it was considered an impossible equation and so on. And however, it turned out, not really for solving the quadratic, but turned out for solving the cubic, that some kinds of cubics you need to solve via, there's a formula, but halfway along the way it yields these so-called imaginary numbers and ends up with a real number, but still there's an imaginary number along the way. And how's that? So they had to decide, okay, let's just call it that, call this square root of -1, call it I, and see how far we can go with this. They call it an imaginary unit. That's unfair. Turns out they can visualize it quite easily. If you have a number line with 0, 1, 2, -1, -2, and so on in both directions, this I can be thought of as sideways, as neither positive in the forward direction or the backwards direction, but a sideways direction. The mathematician Gauss therefore said that really these should be called lateral units. And therefore, I presume the whole system of numbers a plus ib should be called planar numbers. We call them complex numbers, a plus ib. You can think of these going over a and up a distance b, a two-dimensional number, like in rectangular coordinates. All right, now we need to define addition, subtraction, multiplication, and division on these complex numbers, and it's best to do it arithmetically in terms of a and b, and geometrically in terms of the point on the plane. We'll do it both ways. Okay, first, to add two complex numbers, you add these real parts, a plus c, and you add these imaginary parts, b plus d. Add real and imaginary parts in parallel. Okay, and in terms of the geometry, if this is the complex number 0, and this is the number z, and this is the number w, then it turns out that z plus w is this fourth point on this parallelogram. 0z and w to z plus w are parallel lines. 0 to w and z to z plus w are parallel lines. So that's the parallelogram law for adding complex numbers geometrically. And I suppose you could call this the parallelism law for adding them algebraically. A plus ib minus c plus id, you subtract the real and imaginary parts. A minus c here, b minus d here. All right. It's sort of like the, geometrically, it's sort of like the addition rule. Only you have to add a negation step. If here's 0 and here's z and here's w, then minus w is the same distance, same length as w, but in the opposite direction. So there's negative w. Then z minus w is z plus negative w. So you draw this parallelogram here, and here's z minus w. I call this the D rule because, you know, it makes a letter D on the plane, and D stands for difference. Now, multiplication is a little more complicated. We have to assume that it works more or less the same way as it does with real numbers, and see if it's consistent, and it is. To do it algebraically, you multiply these out, you use FOIL. First, outer, inner, last. AC is first, AID is outer, IBC is inner, IBID is last. And we also use that I squared equals -1. So you have AC plus I squared BD from here, and that comes out to AD minus AC minus BD. Then there's a common factor of I. Again, we assume that the usual rules of distribution will work and get I times AD plus BC. So that is the product of two complex numbers. Okay, using FOIL and I squared equals -1. So for example, 5 plus I3 plus 3 plus I2. Oh, by the way, I prefer to put the I in front of the number because I think the I is really more like a sign. plus or minus than it is like a number. However, it's common enough to regard it as to write it as a plus bi as well as a plus ib. It's 5 plus I3 times 3 plus I2. 5 times 3, okay, here. I3 times I2 is minus 3 times 2, here. I times 3 times 3, I times 5 times 2. Okay, here it's 15 minus 6 is the real part, plus I times 10 plus 9. After a bit of arithmetic, it's 9 plus I19. Here's a cute one. 5 plus I3 times 5 minus I3. So you have plus and a minus the imaginary parts. Some cancellation will occur. Okay, first is 5 times 5 minus a minus bd is, here's a minus 3 times a minus I squared, so minus 3. And here, I times 3 times 5 goes here. Minus I times 3 times 5 goes here. So it'll be 25 plus 9. It's the real part, plus I times 15 minus 15. These cancel out. So all you get is a purely real number, 34. In general, if you have a plus ib times a minus ib, the iab and the minus iab cancel out. ib times minus b, it's minus negative is plus. So you get a squared plus b squared. Remember, I believe earlier on I mentioned that you can't factor this in the real numbers. Well, here's how you factor it in the complex numbers. So for example, 3 plus 4i times 3 minus 4i. Oops, here I'm writing I afterwards, whatever. Okay, it's 3 squared plus 4 squared is 9 plus 16 is 25. 7 minus 2i times 7 plus 2i. Well, 7 squared plus 2 squared. 49 plus 4 makes 53. Now this fact is useful for dividing complex numbers. Because if you have 1 over 3 plus 4i, this is basically a form of rationalizing the denominator. We're going to remove the square root of negative 1 from the denominator. And we'll do that by rescaling by conjugate of the denominator. We rescale. Now that we multiply numerator and denominator by the same thing. The same thing is the conjugate of the denominator. 3 plus 4i, its conjugate is 3 minus 4i. The point being is that their product, 3 plus 4i times 3 minus 4i, is 3 squared plus 4 squared, or 25. Meanwhile, in the numerator, you just 1 times 3 minus 4i, it's 3 minus 4i, or 25. And then you rewrite it as 3 25ths minus I times 4 25ths. And that concludes writing this reciprocal. Here we have a division. 3i plus 3i over 7 minus 2i. Okay, again, we'll rescale, but multiply above and below, by the conjugate of the denominator. The conjugate of 7 minus 2i is 7 plus 2i. Just flip the minus I to the plus I and vice versa. Okay, this denominator, it'll be 7 squared plus 2 squared, 49 plus 4. The numerator, after a bit of arithmetic, is 1 plus I 23. All that over 53 equals 1 53rd plus I times 23 53rds. Okay, more examples. 6 plus I times 9 plus 3i. Okay, this is just addition, so we'll add the real and imaginary parts. 6 plus 9 makes 15. Minus 1 plus 3 makes 2. 15 plus I times 2. Here we have 7 minus 3i minus 4 plus 2i. Okay, again, this is a subtraction, so we'll subtract the real parts. 7 minus 4 makes 3. Subtract the negative, the imaginary parts. Negative 3 minus 2 times I makes 3 minus I5. That's done. Product, 2 plus I times 3 minus I. Okay, do FOIL. First is 2 times 3. Outer is minus, then 2 times 3, plus minus 2i, plus 3i from the inner, and then I times the minus I comes out to a plus 1. 6 plus 1 times I plus 1 is 7 plus I. Okay, great. There we have a square of 2 plus I. Well, okay, that's the 2 plus I times 2 plus I, this multiplication. And do the FOIL thing. 2 times 2 is 4. I times I is negative 1. 2i plus 2i here. End result 3 plus I times 4. Here we have a ratio. 3 minus 2i over 4 minus I. We'll rescale, multiply above and below by the conjugate of the denominator. 4 minus I, its conjugate is 4 plus I. So this 3 minus 2I over 4 minus I times 4 plus I over 4 plus I. Now, okay, if you work out the numerator, 3 times 2 is 12, minus 2I times I is minus a negative 2, minus 2I times 4 is minus 8I, 3 times I is 3I. After a bit of arithmetic, that's 14 minus I5. And the denominator, 4 minus I times 4 plus I is 4 squared plus 1 squared. 16 plus 1. And so after a bit of work, it's 4/17 minus I times 5/17. Here we have 5 plus 9I over 1 minus I. So rescale by 1 plus I, the conjugate of the denominator. 1 minus I times 1 plus I is 1 squared plus 1 squared, which is 2. 5 plus 9I times 1 plus I after a bit of arithmetic is minus 4 plus I, 14. Dividing both of these terms by 2, you get negative 2 plus I times 7. Here we have the square of 4 minus 8I. Well, again, a square of a number is a number times itself. Also, you use the rule a squared minus 2ab plus b squared. All right, churning this out after a bit of work, it's minus 48 plus minus 64I. Here we have two related problems, the square of 2I and the square root of 2 plus I. Well, the square root of 2I will be 2 squared times I squared, and I squared is negative, 2 squared is 4, so you get negative 4. Here you have the square of 2 plus I. Well, the square of a sum is square plus twice product plus square. So that's 4 from here. Here's 4I from here is minus 1 from here. Combine like terms, and you get 3 plus 4I. Okay.